As you'll have seen from the pictures earlier, not all capacitors are parallel plates. Often they are cylindrical, and you see the equation for the capacitance of a cylindrical capacitor at the side. We also have there the capacitance of a spherical capacitor. I won't derive them for you, but you could look it up in the textbook if you're interested to see how they come about. Now to calculate how much energy is stored in a capacitor. We'll work it out by looking at the amount of work that has to be done to move charges across from one plate to the other. Of course, you remember that as the charges are moving across, the charge on each plate is growing, the electric field is getting stronger, and so more work has to be done. Now, to work out the energy stored in a capacitor, we look at the parallel plates. We'll say that the top plate is minus Q and the bottom is plus Q. Now, this is their charge at one particular moment because we are getting little bits of charge, and of course we call those dQ, and we are moving them across from the negative to the positive plate, and that means we are storing energy. Now we will count the distance between them as D, and we will say that the potential difference between them there is delta V. Now the things we know that capacitance is Q over V, and so we have V will be Q over C. Now, this charge, little dq, is going to keep moving across one after the other until we have a total charge that we will call capital Q. So we're moving dq, that means we're doing work on it. So the energy that will be stored is the small amount of work being done to move that single charge, dq, through a potential difference, delta V. Now the other thing we know though is that V equals Q over C. So we have dW equals Q over C times dQ. Now that is the energy stored by moving one small bit of charge, dQ. So the total energy, we'll call it U, that will be the energy stored once we've done the total amount of work, will be the integral from zero charge up to a maximum charge of that small amount of work for each charge. And that gets us from 0 to Q of Q over C times dQ. Now the integral of Q to the power 1, well, first thing we'll do is take the 1 over C out the front since that's the constant. The integral of Q will be a half Q squared. So we've raised the power by 1 and then we've divided by that 2. And that is from 0 to Q. So that will be Q squared over 2C minus 0, of course. And Q we can say equals C times V. So we'll say C squared V squared over 2C. The C's cancel out and we end up with an expression for the energy being a half C V squared.